Hi class, we are on the next section of chapter 8. This is section 8.2. We're going to be talking about the trig form of complex numbers. This is actually the polar form of complex numbers. The polar form of complex numbers are written in terms of sine and cosine. So here is the cover sheet to let us know what we're covering. Right, so we're going to look at the vector representation of the complex plane, which is very simple. Actually, it's not hard to graph complex numbers. Graphing complex numbers is just like graphing any regular coordinate in the regular rectangular Cartesian plane. So it just comes with coordinate pairs, and we graph the coordinate pairs. We'll look at the angles that they form. We'll look at their sines, their cosines, their lengths, all that kind of stuff. So this is a little bit of us getting familiar with some of the terms of the complex numbers and looking what complex numbers look like when you graph them. Okay. So first, let's talk about the horizontal axis. So when you graph a complex number, so remember your complex number has two parts. It has the real part, which we call A, and it has the imaginary part that we call B. So what we do is we take that A and B and we turn them into a coordinate pair. My x-axis will be replaced with the real axis. So whatever my number A is, that now turns into my x coordinate for the regular rectangular coordinate system. My imaginary value B turns into my vertical coordinate or my y coordinate. So instead of having xy as a coordinate pair, we look at a b. So if I have the number, let's say 2 plus 3i, that means that in the coordinate plane, I go over to 2 and up to 3, and I draw my vector basically. Okay, so all of that will be reviewed here, so we'll run through this slide pretty quickly. Okay, I have an x-axis, which we call the real axis. This x will be replaced with an a, right? Because it is my real value. We actually write RE to represent the real axis. My vertical axis is the imaginary axis. This y will be replaced with IM. So we call this RE and IM, RE for real, IM for imaginary. Okay. Each complex number is ABI, determines a unique position vector with the initial point at the origin and the terminal point at AB. Okay. So here if I do 2 minus 3i, I go, my real portion here A is a 2, so I go to 2. And then my imaginary part is -3, so I go to -3. And then that's the end of my vector. And now I have a vector. Okay. And again, with any vector, we now have an angle that is created. We have a cosine length, we have a sine length, and we have the length of the vector, which are all important things that are going to come together when we start talking about these and doing math on them basically. Okay. So the sum of two complex numbers is represented by a vector that is the result of adding two vectors together, right? Where those two vectors that you're adding together are representations of the two complex numbers you added together. Okay, so 4 plus I can be represented by 4 on the x-axis, 1 on the y-axis. If I want to add 1 plus 3i, well, that's 1 on the real, 3 on the imaginary. Okay, and so if I add these things together, it would be just like adding like I normally do, right? So for vector addition, we add the x terms. For complex numbers, we add the real terms, right? On a vector, I would add the y terms. On complex numbers, I add the imaginary terms. Okay, so here I get 5 plus 4i, which is the same thing as if I did the parallelogram rule or the tip to tail rule. Okay, so here we want to find the sum of 6 minus 2i and -4 minus 3i. We've already done this quite a few times in the last section. So 6 minus 4 will be a 2. -2 plus a -3 will be -5. So I'll have 2 minus 5i, and we can graph these as the sum of vectors. Okay, so 6 minus 2i, -4 minus 3i. So again, go to -4, go down to -3i, okay, or to -3, I guess, and then we can draw our parallelogram. Okay, which you can probably see a little bit of here, and then my center value. My resultant will be the diagonal of that parallelogram. Okay. So all things that we're familiar with, we're just throwing them together. We're familiar with adding vectors. We're familiar with the geometry of adding vectors. We're familiar with adding complex numbers. So we're just throwing those three things together, and we're saying that they're basically the same thing, which they are. Okay. So now we have relationships. So remember, when we have a triangle, x represents the cosine. So my a value is the cosine. My y is the sine. And remember, for a unit circle, the radius is 1. So if my radius has a length of r, then this x is just r times the cosine of this angle, right? Everything gets pushed over by a factor of r, okay? So x is r cosine theta, right? So you're multiplying the cosine of this angle times the length of the radius. And then same thing for y. Y will be r sine theta. Okay. And r, the length for a triangle, is x squared plus y squared. So now we know that x and y is really replaced with the a in the complex number, and y is replaced with b. Okay, and r will be replaced with the length of the vector that's created. Okay, which we'll see later, but we call this the modulus, right? So what we were calling before as the magnitude or the length of the vector in complex numbers, we call the modulus, right? So there's several names for the same things depending on what it is you're referring to. Okay. Remember, if I want to find theta, I would do tan inverse of y over x as long as x is not 0. Again, if you remember me griping about this, they always write it as tan theta is y over x. But it's always easier to think of it as theta. You only use this to find theta, right? So it's easier to say theta is tan inverse of y over x. Okay. So now let's look at that in terms of a complex number, right? Which we'll call the polar form of our complex numbers. So remember, complex number is a plus bi. So in this case, we're saying x plus yi because x is the real axis and y is the imaginary axis. So when we put those things together, we get r cosine plus I r sine theta, because remember, x is r cosine theta. Okay. X is r cosine theta. So when I have a plus bi, I have r cosine theta, which is the a, plus bi, which replaces with r I sine theta. So when we put those together, we can take out the common factor of r. Okay. So the expression cosine theta plus I sine theta is sometimes abbreviated as cis theta. Now, I'll say this, when I teach calculus, all my calculus students, they like to write this because they want to be fancy. This is not a standard notation. This does not come up too often. People don't really use this, and it actually gets on my nerves when I see this when people are trying to do their math. But it is semi-common. It's not very common. However, some people use it, some people don't, right? So just know that some people want to see this r cosine theta plus I sine theta format. Me, I'm fine with whatever in this class, but just know when you move on to different courses, pre-calculus, calculus, DiffEQ, whatever other courses you end up taking, this is not a common notation, okay? Using this notation, r cosine theta plus I sine theta would be rewritten as r cis theta. Okay. R is an absolute value. Okay. If it ends up being negative, we take it as being positive. That's really the use for it, because r is a length. We need it to be positive, right? So we call this the modulus. It's the length, right? The length of the vector. It's the length of the vector of x plus yi, and theta is called the argument. It's the angle created with the real axis, but we call that the argument. Okay, so theta is the argument, r is the modulus, the length is the modulus, and the angle is the argument. Important to remember. And so for this example, we want to express 2 times cosine 300 degrees plus I sine 300 degrees in rectangular form. Okay, so we know what the modulus is. We know what the angle is, so we want to get this into a value of a and a value of b, right? So 2 sine 300 degrees is my b value, right? 2 cosine 300 degrees is my A value. So what I want to do is I want to find what cosine of 300 degrees is, right? Which is easy. This is a standard reference angle, right? It's the same as cosine of 60, except for this will be positive and this will be negative because we are in quadrant 4, right? 300 degrees is in quadrant 4, and the reference angle is 60 because it was 360 I'd be on the x-axis. So I need to take cosine of 300 degrees, multiply by 2, that's my A. I take sine of 300 degrees, multiply by 2, and that's my B, and then I can write this as A plus BI, right? So it's actually very straightforward to go into the form that we want, right? So I have cosine of 300 degrees is 1/2, sine of 300 is negative root 3 over 2. We're going to end up multiplying both of those by 2, so cosine, so I'm going to have 1 plus, or 1 minus root 3i, or I root 3, okay? 1 minus I root 3. It's pretty straightforward to go back and forth. Your calculator will do this, but as you notice, it'll give you a decimal approximation. I do not want decimal approximations in my class. I've said that several times at this point for those of you who have taken my class. So I will definitely want the exact values for these things. If you give me the decimal approximations, I will take points off of your scores. So do them exact, please. Okay. So how do we do this, right? So let's write this down in steps. Okay. We can sketch our number in the complex plane. Again, this x is the real, this y is the imaginary. So writing it as x plus yi helps us to remember how it is we're supposed to graph it, right? Step 2 is I want to find the modulus, okay? I want to find the length of my vector, okay? After I find the length of my vector and I have the graph, I'd like to find the argument, right? So remember the argument is the angle that's created because I need to write it as cosine of this angle and sine of this angle. So I would use tan inverse of y over x to figure out what my theta is, okay? So again, make sure we choose the correct quadrant so that you have the correct signs and the correct angles. Sorry, you already have the correct signs, so make sure you choose the correct angle so that it makes sense, okay? You don't want to find something in quadrant 1 if it's really supposed to be in quadrant 4, right? You have a wrong angle value. So very, very important to make sure you choose the correct quadrant, otherwise your polar form of your complex number is completely incorrect. Okay, so let's go ahead and do an example. Okay, so remember what it is that we want to do. First, we're going to graph, right? So we're going to go negative root 3 in the x direction and then up 1 in the y direction. We'll use this x and y values to find out the length of the vector, and then we can use tan inverse to find out the angle that's formed, and then it's very easy to write it in our polar form. Okay, so we use radians here. We generally use radians, so the examples were in degrees, but generally radians is the measure that you use. Okay, so here we're going to sketch the graph. Okay, so again, negative root 3 is my x, and then up 1, create the angle, or I'm sorry, the vector there. Use the definition of modulus, so square negative root 3 and add it to the square of 1, so 4, right? So this length is going to be 2, okay? Okay, so you're going to get 3 plus 1 is 4, square root of 4 is 2, right? So my modulus is 2, the length of this vector formed in the complex plane is 2. So now I need to find the angle, right? So I'll use tan inverse of y over x. So it'll be tan inverse of 1 over negative root 3, which can be expanded and thought of as tangent of negative 1/2 over root 3 over 2, right? Because that's something that we're familiar with, sine and cosine wise. And so that gives me an angle of 30 degrees, but it's on this side, so it's going to have to be 150 degrees. So let's go ahead and look at what that looks like here, right? So 1 over negative root 3. So you can think of this again. The way I would think of it is 1 over 2, and this is as negative root 3 over 2 with the 2's both canceling because they're in denominators. Then you just think of the angle that goes with that, right? So the reference angle here is going to be pi over 6. So it's like the 150 degrees with the reference angle of 30 degrees. And again, we're in radians, so that's pi over 6 for us. Okay. So here it shows that it's in quadrant 2. So again, that actual angle is pi minus pi over 6. So that's going to be 5 pi over 6, which is, again, 150 degrees, right? So that's the actual angle. The reference angle we'll be using is the pi over 6, just making sure we have the correct positives and negatives. But when we write this in cosine and sine, we use 5 pi over 6 because that's the actual angle, right? So here, you don't have to write it with the r factored out. You can write it as 2 cosine 5 pi over 6 plus 2I sine 5 pi over 6, and that's fine. But again, since the r is common, you can factor it out, and there's nothing wrong with that as well. Okay. So then we want to write it in the cis notation. It would look like this: 2 cosine I sine 5 pi over 6. All right. So for the next example, let's do the same thing for negative 3i. So here you notice we will be on the x-axis because we have no a term. So we'll do the same thing, but this time we'll do degree measures, right? So just looking at this, negative 3i means that we're going straight down to negative 3. So we'll be on the angle of 270 degrees, right? Because we're on the y-axis and we're going down. So that's nice. Okay, it's easy to tell. Okay, and so then the length of this also is just going to be 0 squared plus 3 squared, square rooted. So it has a length of 3, which is very apparent because it goes down by 3. Okay, so the argument and the modulus is easy to find. So we would write this as 3 cosine 270 degrees plus 3 sine 270 degrees. Okay, sorry. All right, very standard, very easy, or 3 cis 270. Okay. All right. So here, we're converting between trig and rectangular forms using calculator approximations. So we want to write each complex number in its alternative form. Here, it's allowed, it's expected of us to use calculator approximations as necessary, right? So if we have bad angles, for instance, we would use our calculator, or perhaps we have a bad modulus that we need to find, we would use a calculator, right? So again, here we end up with a bad angle, right? We don't really know what cosine of 120 is. We could find the exact value by using some sort of sum and difference formulas, which are terrible. Nobody likes to use those. You'll probably never see them again in your life after this class, or even use them again in this class, to be honest, except for a final that might pop up, and even then I probably won't ask them because they're not used often. But we could find this exactly if we use the sum and difference formula. So instead we're going to use a calculator approximation because that's way easier, right? So here I have 6 times in cosine of 125 gives me this radian measure. Sine of 125 gives me this measure, and then we just multiply that by 6. Okay, so then that's my approximate value for this polar form, right? It's now in its complex form. So it's really just multiplying everything out, you guys, right? So when you have a nice angle, you're still doing the same thing. You're just multiplying everything out. Okay. Here, 5 minus 4i, so it's in complex. So we want to get into our polar form. So what we're going to do is we can graph it, or we can just recognize that the length is 5 squared plus 4 squared being square rooted. So that's what, 25 plus 16 is 41. Square root of 41 is a prime number, so we're not going to be able to find that. So when we want to find the angle, we're going to have to use our tan inverse, and we can get an approximation for tan inverse, okay? Because we're not going to find a nice degree here, so we'll use our calculator to find tan inverse of negative 4 over 5, right? So we got negative 38.66 degrees. And so now when we write this, we can write this as root 41 times cosine of negative 38.66, or its reference angle, really. So negative 38.66 degrees means that I have 200, no, 322, 42, some number, right? So 321 and 34 degrees. So I'll write root 41 cosine 321.34 degrees plus I root 41 sine 321.34 degrees. Okay. We write it as a cis, which is a lot easier. Okay. So now we're going to get into an application of polar forms, complex numbers, which is called fractals. Okay. So fractals are super interesting. If you've never seen them, I'm going to pull away for this for a second. But basically what a fractal is something that repeats itself. So no matter how much you zoom in, you will get into a repeating form of what it is that you have. Okay. So the ones I'm going to show you real quick. First one is going to be called the Koch snowflake. Basically what a fractal does is if you want to draw it yourself, then what you do is you basically start a pattern, and every time you redraw a line in that pattern, you draw that pattern on that line that you just drew. Okay, so it's very reiterative. It'll make sense when you start to see this step-by-step process I'm going to show you guys. So as you can see here, there's several examples in nature of what a fractal is. So this is just from plant growth, right? These are some sort of a cacti, right? So as you see, it's a repeating sort of pattern that happens, right? So it's very common in nature to see fractal patterns, and these are represented by the complex plane, right? So we'll talk about how to build one of these. It's called the Julia set. I did not show you the Julia set, but it's a very common fractal. So is what's called the Mandelbrot set. There's a couple of very common ones: Sierpinski's triangle, the Koch snowflake, which I just showed you. So now we'll just talk about a couple iterations of the Julia set using complex numbers. In the glass. Okay, let's go ahead and get started. Okay, so the image of the Julia set looks something like this. So if you were to Google Julia set and then go to an interactive map of the Julia set, let's say you wanted to zoom in here, what would happen is that your image would just start to repeat itself. You would zoom in, you can zoom in an infinite amount of times. You can never stop zooming in. And the pattern goes through several iterations that then start to repeat itself. It's very interesting. And again, as you see, they're represented in nature quite often, right? So if we want to determine if a complex number is represented in the Julia set, we're going to perform a sequence of calculations. Okay, we're going to take z squared. So z is this complex number, a plus bi. So we're going to square this complex number and subtract 1 from it. Okay, then we're going to square that first result and subtract 1 from it. Then that second value we got, we're going to square that and subtract 1 from it. So every time we find a value, we're going to square it and subtract 1 from it. And the graphs of these things, right, when you graph them in the complex plane, will start to create the Julia set. Okay, so let's go ahead and start. So if the absolute values of any of the resulting complex numbers that we had here are more than 2, then we don't use them. Okay, so we only use the values that are at most the length of 2. And that's our set of values. Okay, so otherwise z is part of the set, and the point AB should be shaded in the graph. So we'll go ahead and do a couple of iterations. Obviously, we're not going to create this entire set, but I'll put a link to an interactive Julia set at the end of the link so you guys can play around with it a little bit. All right, so we want to determine whether each number belongs to the Julia set. So first is z is basically just 0, right? 0 plus 0i is 0, so we're going to start off with 0. So that's going to be fine. So z squared minus 1 is going to be minus 1. So that'll be in the set. Minus 1 squared will be 1. Minus 1 will give me a 0. So that'll work. Okay. Z squared will be 0 squared. Minus 1 will be a negative 1. So you see, we'll start to repeat 0, negative 1, 0, negative 1, 0, negative 1. Right? It's a repeating form sequence of numbers. Okay. So this will be a Julia set. Right? So the absolute values are either 0 or 1, which do not exceed our limit of 2. So 0 plus 0i, 0, is in the Julia set, and the point 0, 0 is part of the graph, right? So 0, 0 would be part of my graph of the Julia set. Next, we'll look at the next point, 1 plus 1i. We're going to do the exact same thing. So I'm going to square this. So remember, you're not just squaring each term. You have to expand this. So 1 plus 1i times 1 plus 1i. Or you use the perfect squares formula. So that'll get us, so z squared minus 1 will get us 1 plus 1i plus I squared. Okay, minus 1. So then we'll have to simplify this. So this is really going to be negative 1 plus 2i, because this 1 and I squared is going to cancel because this is negative 1. Right? So the absolute value of this, the length of this, the modulus of this is root 5. Square root of 5 is more than 2, right? Because square root of 4 is 2. This is more than square root of 4. It's larger than 2. So this value instantly is not in our set. We don't even have to continue with the rest of the calculations, right? Okay, and that's how this works, right? So you check these values, and once you reach something that's not there, then you ignore it.